In this semi-random episode, I'm going to be talking about impedance, specifically about the impedance of your IEMs or your headphones, and also the impedance of your amplifier. No matter what, if you're listening to audio through IEM or headphone, you have an amp. It may be built into the device. It may be an external one. It could be on a little dongle. It could be a standalone kind of thing, but it is going to have an output impedance. When you plug that in, the headphone, the IEMs that you're listening to, anything like this is going to have its own impedance. And these things interact. So what I have on here, and we're going to unpack how we come up with things like this, and is the impact that for example, cranial daybreak, the impact on its frequency response of different impedances of the actual amplifier there. So as you can see, this is going plus and minus 4 dB on this scale. There are some pretty big swings that we can actually have. So let's get into it. First off, I'm going to get it so you can actually measure this yourself. Because when other people have talked about this, what I've seen is that there are things like, hey, yeah, this is the impact of it, but you have no way of actually knowing what the impedance of your rig is. You've got a motherboard, you've got a laptop, you've got something. What is it? So how do you know? And I'm going to show you how for just a few bucks, you can actually go and do this. So I don't care where you get it from. I'm trying to give you a couple of options here. Parts Express sells these things. Of course, places like AliExpress sell the things. Amazon sells it. You can get it in a whole eBay. You can get these things in a whole bunch of different places. So by far, I think the easiest way to go about doing it is to get this little device here. What this is, you can search for 3.5 millimeter screw terminal connector male 3-pin. Here's what it looks like. There it is in the flesh, as it were, here. Because this can then go and plug actually into your device. As you can see attached on this right now, I have a little resistor. This one happens to be 10.2 ohms, marked as 10 ohms. So you're going to need something like this, the thing to plug in, and you're going to need some kind of load. I suggest actually getting an assortment here. You can get the one I have on here is a 1/4 watt resistor. You can get 1/2 watt. You can get 1 watt. The key thing to really do when you're searching is you want metal film. Metal film is important because A, it's a little bit more accurate, more precise. B, it's a purely resistive load. The cheaper carbon film ones can have a little bit of a complex load to them here. So get yourself a little kit. You can get just the one if you want. If you want to be able to measure the power of your devices, maybe you want more than the 1/4 watt, maybe you want the 1/2 watt or the 1 watt. Heck, even getting like 2 watt ones or whatever, it's a buck more. It's not a huge investment here. So we've got a couple bucks for this. We've got $5, $6, $7 or whatever for the resistors. All right, well, so far we're not exactly breaking too many banks. And then you're going to need one of these two things, either a multimeter or a handheld oscilloscope. I've got both of them here. Multimeter I've had for ages. And this is actually even a cheaper little portable handheld oscilloscope that I'd picked up many years ago off of Amazon. You don't need them both. Either one is going to do. This multimeter I think I picked out here, this one is something like, it's under 20 bucks. It's like 19 bucks or something like this. The oscilloscope I have down here, it's 37 bucks. The oscilloscope's going to be a little bit more useful for a number of kinds of things, but don't want that? Fine, don't need it. Key if you pick up the multimeter is to get one that has some voltage scales that look like this. There are a few of them out there that are like 15 bucks that really just have like a 400 volt scale. And we're going to be measuring things on the order of like a 1/2 volt, 0.7 volts, volt and a half. We need to actually make sure that it's got a decent resolution and everything down at that point. So you're going to want something that's a little bit, that has something like here. This has got a 4 volt scale. Perfect. Okay, if it's 2 volts, if it's 5, I don't care, but something down in that kind of range so that you're actually going to have some resolution and everything on it. And then if you actually want to go and have the ability to actually then do the next level of things, not just measure the output impedance of your device itself, but actually get the complex impedance curve of the device that of your IEMs or headphones, you're also going to need then a little bit more. You're going to need to get some probably a female version of that same kind of connector so that you can actually plug your IEM or headphone into, and you're going to need some hookup wire. Again, grand total, it's like $2 or $3 for each one of these little bits here, the connectors, and then it's a few bucks also for the hookup wire. We're not exactly breaking the bank. After that, what do you need? Well, you need some free software. That's about it. In fact, easy way to go and do this kind of thing is just go to Audiophile. Fantastic site for all sorts of things, being able to help you with your own parametric EQ and everything. Yeah, we're just going to use it as a test tone generator here. What we're going to do, we're going to go there, we're going to turn, particularly if you're using a multimeter, we're going to actually then go and set the frequency that it's going at here to be 60 hertz. And we're going to do that because your multimeters are actually going to be accurate here. Mine, for example, starts to fall off on its estimate around 500 hertz or something like that. There's nothing magic about doing this at 1 kilohertz. If you're using an oscilloscope, I don't care, use like a kilohertz if you feel like. But in any case, set this to 60 hertz, turn off the limit duration, crank the volume here to be at 100%, and then probably in your actual like system volume on your laptop, your desktop, whatever you're testing here, dial it down to about 90% or something like this. We want it to be nice and loud so that we're above any noise that you may have, but that's really all we actually want to have here. We don't want to risk having it clip and get to be really distorted. And by clipping, I mean, what we want to do is if you had an oscilloscope, it should look like a nice sine wave like we have here. It shouldn't look like the one on the right. The one on the right is showing clipping because I had the volume set too high. Okay, so that's what you need on that. You can also use REW, Room EQ Wizard, and if you want to measure the actual impedance curves of your IEMs, you're going to need REW for that. You can also, if you don't feel like any of these for some reason, if you have a test tone that's been downloaded onto your local machine as just a sound file, YouTube test tones, I really don't care. You need it to go buh, and that's about it. All right, so here's what this looks like. This is me testing my motherboard, an Asus TUF Gaming B650 Plus Wi-Fi. And I'm testing using both of these setups so you have some ideas what this actually looks like. So I start playing the tone, and I have my little device. My device is plugged in this case to then the top mounted headphone jack. I'm playing the tone, and as you can see on here right now, I have the resistor so that unlike right here where both leads are actually plugged in, you can see right here, one lead is plugged in and the other is just dangling up there in air. I don't care. And I then hooked my test leads up between the common port. These have 3 things on here. One of the things is in common. It's kind of like ground. And then you have a left channel and you have a right channel. And of course, the 3 screws, there's a common labeled ground, and then you have a left and you have a right. And you're probably playing in stereo. So in any case, tone is going boom, and you are, well, that's not 60 hertz. In any case, the tone is going and you're just measuring what is the voltage. I have my meter set to measure volts in AC, not DC. Try to measuring DC direct current, you'll get nothing. AC, hey, look, it's going and it's reading out that sine wave. And I read out here is reading 1.353 volts. Take a picture or write that down. Then you go through and you say, hey, hook it up so that actually the resistor is now this 10 ohm resistor that you have gotten out of that kit. Oh, I should have mentioned, by the way, on that last one, what you really want out of the kit for this part is something on the order of 10 to 20 ohms, something that's in the ballpark of the headphones and IEMs that you're going to be measuring on here. So I'm using a 10.2 ohm. It's marked as a 10 ohm, using that to actually go and read this. And as you can see, the voltage is way down from what it actually was with no load. If I have this 10.2 ohm load, I'm down at 0.144. It's about 1/10 of the voltage. Ooh, that dropped a whole bunch just by putting a load on here. If you have the oscilloscope, it's the same basic setup here where you say, okay, look, I take the leads of the oscilloscope, I plug them in and I see what the voltage is. If it's reading 3.76 volts with the load not hooked up, and it's reading 0.399 volts or 399 millivolts with it on there. You may be saying to yourself, wow, this guy's an absolute idiot because he's doing something where he's getting 1.3 volts out of one meter and 3.76 out of the other one. Guy has no idea what the heck he's talking about. Well, okay, yes, I kind of do, because the meter reads in volts RMS, root mean squared, and the oscilloscope is giving me the readout in terms of peak to peak. So it's not like a kind of average sort of thing here. It's the distance from the top to the bottom. And we know in electronics here that the voltage peak to peak is 2.828 times the volts RMS. So it's almost 3 times as big. And yeah, that's the exact difference there. Doesn't matter which one you read it in, just be consistent. Okay, so if we then go and take a look at this, we can now see that, all right, we can use these two numbers and the value of that resistor to actually then go and calculate the output impedance. That's it. You're done. We've done all of the measurements that are actually needed to go and do this. And so what do we get? There's a little formula here. You take the voltage without load, that 1.353, subtract the voltage with load, subtract that 0.144 there. Take that, multiply it by the resistance of that you were using onto that load, 10.2 in this case, divide it by the voltage under load, 0.144, and do that little math, and you get 85.6 ohms. By the way, over here are the RMS values from the scope's peak to peak. So my motherboard is giving me an 86 ohm output impedance. By the way, over here, this is if you're trying to just do this on your own in a spreadsheet, the exact formula that I'm using to go and pull that off. 86 ohms. What does that mean? What does that do? I'll give you a hint. It's not good. Because we can even do things like test a whole bunch of other things like, oh, I don't know, this little J-Cali JM6 or the Apple dongle. This guy's $10. The J-Cali is like $17 or something like this. Run the same thing. The JM6 Pro is at 2.2 ohms and the Apple is at 0.25 ohms. Yeah, that's a lot different than 85. In fact, I tested a whole bunch of things. I tested some things I had on here. I shit Fulla, shit Magni, 14-inch M4 MacBook Pro, Hibi R4 DAP. All of these are under an ohm. Another little Moondrop dongle we had around, 2.5. A Microsoft Surface Pro 3, 55. An MSI GS65 Stealth laptop, 1.9. Framework, 13, 58. Okay, so what you kind of see here is that there's a cluster of them that are doing really, really well, and they're getting very low numbers, and then others that are decidedly higher. Well, yeah, I mean, Apple markets all sorts of stuff about being able to drive all sorts of kinds of headphones off of it. My MSI old GS65 Stealth had audio by Dyne Audio, all sorts of stuff. And yeah, we see a pretty broad range. But what does it actually do? Well, okay, here's what it does. The problem in terms of what's going on here is that the output impedance of the amplifier, right here listed as R1, forms a voltage divider with your headphones. Okay, what the heck is a voltage divider? What does any of that mean? What it means is that you have some voltage that's coming out of your amplifier that's supposed to be driving your headphones, but the combination of the two of these is then going and cutting down on the voltage here. The output that your headphones are actually seeing is equal to the resistance or the impedance. By the way, impedance is just resistance, but across frequencies, it's looking at the complex sort of aspect of resistance. So sometimes you see Z's, sometimes you see R's. In any case, it's saying that resistance divided by the sum of them times the original voltage here. So if you look at this here, if this earphone, if the headphone resistance or impedance here is a lot larger than the amp, you have like 500 over 0.1 plus 500 is pretty much 500 over 500. So 500 over 500 would be 1 times the voltage input. Yeah, you're getting the same thing out that you were putting in. That's this voltage divider. But let's say instead that they were equal. Okay, let's say you have a 20 ohm output impedance of your amplifier and a 20 ohm headphone. 20 over 20 plus 20, 20 over 40, 1 over 2, that's a 0.5. Oh, geez, wait a minute, I'm getting half on my output what I actually had on my input? That's this. By the way, this ratio is called the damping factor in audio things. They talk about the impedance of the speaker divided by the impedance of the amplifier, and they look for numbers like at least 10 and ideally even maybe 100. So yeah, we start to then see that you're at least cutting down on the signal. And some of this then starts to get to like, oh, is this why maybe some of these headphones sound kind of quiet on here? Can happen if the impedance is too low or too high. But yeah, this can be one of the reasons why this is happening. So, but what does it really do? Well, okay. I've mentioned already this idea that this is changing over frequency, that we could talk about resistance, and resistance would just be at DC, direct current. What is overall, how much is it impeding then the flow of your electrons, the flow of your signal here? Well, we also, though, have in things like our headphones here, it follows a curve, which is why it's an impedance. So here are 4 IEMs that I measured using REW earlier here that I just happened to have around. One is the Moondrop Starfield. It was the earlier version of the Aria. And you can see on this, it starts off at about 32 ohms. And as we go across here, there's a little bit of a peak at around 3 kilohertz and then goes down. This peak, by the way, in the impedance is actually at the resonant frequency, or the FS of the driver in Thiel small parameter land. But you can see it's pretty darn constant, except for this little peak. Take some of the others. Take this hexa. It starts off at around, just under 19 ohms, does that, slowly ramps up, but then has a big peak around 3K, then drops down, then jumps up again, then drops way down. And the difference between the top and the bottom is almost a 2-to-1. Same kind of thing in the daybreak, but the complete flip in terms of where you're having the peaks. The daybreak and the meta have big peaks toward the base. And then they drop down in the mid-range, and then they bump back up again here. So in all of this then, remember that whole voltage divider thing? If the output is going to depend upon the ratio of, if you're actually hearing, the volume is dependent upon the ratio of the amplifier's output impedance and the headphones, and this is changing by frequency, the output is now changing by frequency. So if you really have it so that the output impedance is a substantial fraction of your headphones impedance, you are changing the frequency response that you're hearing. That is the big problem. And what this actually looks like then is this. So you do a little bit of math and you can see, like, hey, this is that Starfield one, which had a pretty constant kind of impedance. If you take a planar one, it's probably going to be a perfect resistance just straight across. And yeah, we can see that it changes the frequency response a little bit. This is then simulating what 1 ohm, 3 ohm, 10 ohm, 20 ohm, and 80 ohms would actually do to the frequency response. And we can see that with 1 ohm, 3 ohm, nothing's really going on at all. You're never hearing that. Okay, it's a half a dB around, 3K. Maybe you're picking something like that up. But when we take a look at some of the others, here's the hexa. Oh, by the way, quick thing, you notice below 1 kilohertz, it's like it's dropping, and then above it's boosting. It's purely an artifact of the fact that I normed all of this to 1 kilohertz. But in any case, what we then see here is we got to look at the relative bits. Again, following the impedance curve, the hexa here in orange, following that, we can then see that we're getting this complex kind of response. It's actually boosting up all of the mid-range and all of the treble that's going on here. And yeah, with 1 ohm, it's not something that you're really going to be worried about. 3 ohm, no. 10 ohm, oh, we're over a dB here in terms of going and shifting this. Certainly by the time you're at 20 ohms, 80 ohms, whoa, we're almost 4 dB worth of boost at around 8K. So the hexa, and relative, by the way, to overall down here, it's almost a dB fully down from there. So now that's at least 4.5 dB difference between bass and a bunch of the mid-range and then that treble. The hexa sounds really, really different now if I drove it off of my motherboard than if I were to drive it off the Apple dongle. All right. Daybreak. This actually nicely shows why sometimes you'll see little adapters that have a little male and a female, and it's called bass boost adapter, 10 ohms, something like this. This is exactly why they can do something like this, because you see on this headphone, yeah, it is boosting the heck out of the bass. It is going to make this thing sound dark by going and adding that added impedance. But remember, that's what it did on the daybreak here. That's not what it actually did on the hexa. On the hexa with its curve, it's actually boosting the high end. So it's not like these things are always going to be doing any kind of like bass boost. No, sometimes they are and sometimes they aren't. Here's the Cranier Meta. And we can then see again, it's got a similar in some ways, but now it's even making it even more V-shaped. By the way, a neat little thing you can see in all of these. Up here, I'd mentioned that, okay, hey, look, this is the resonant frequency of the single dynamic driver that's used in here. You can actually see by virtue of the fact that there are multiple bumps and everything inside of here, you can deduce, in fact, that it's actually like a three-way crossover and you have multiple drivers and that it's a hybrid kind of thing. You can figure that out by looking at the impedance curve. Okay, so in any case, in this kind of thing here, we can have a couple of big take-homes. First, most earphones have a complex impedance curve. They're going to. Planars won't. Single DDs will be pretty even, well, pretty constant. They may still actually have one real peak and everything in there that could be a lot bigger. If your amp or your headphone jack's output impedance isn't a lot lower than the headphones, it's going to change the frequency response. It will alter it. And it's not necessarily just going to be a bass boost. Sometimes it is. Sometimes it's not. In the case of the Hex there, is boosting the heck out of the treble. Low impedance earphones can therefore be really, really challenging. Like the Zero Blue 2, Mark Super was pointing out to me that, yeah, that's 5.8 ohms. It's going to be really tough to end up having something. Yeah, you're going to have something with a really low output impedance to be 1/10 of that. So it also gives an idea as to why do tube amps sometimes sound a good bit different, or do people talk about matching it? Now, not all of them and everything here, but particularly those that are OTL without a transformer, yeah, they have really, really high output impedance, on the order of 100 ohms quite often. And so hooking up a low impedance earphone to them is going to alter the sound really, really dramatically. All right, if you want to tune out there, that's totally fine. For those of you who want to then get just that little bit more of like, how the heck do I actually measure the impedance curve of something like an IEM here? Let me give that to you here as well. And if people want, I can go into a little bit more detail on it, but this should be able to get you up and going. Here's what you need. In addition to the stuff that you actually needed to measure the output impedance of your amp, you need a sound card or an audio interface that has two channels, like left and right. It's nothing fancier than that. You also need about a 100 ohm metal film resistor. So here I have two of them in parallel because I happen to have them, and they're each about 200 ohms, 220, whatever. In any case, you need then to have something about 100 ohms or so that you can mock up here, and some basic hookup wire. This diagram came from REW's help file, completely just stole it from them, but you're going to use REW to actually then go and do that assessment. That assessment has you do things like say, hey, go hook it up like this, and I'm leaving this on here. Oh, by the way, the thing down here is I just took a little like Y splitter I happen to have that had a 3.5 millimeter female on it, and I cut it, and I'm using that instead of, because I didn't have the female version of one of these. Okay, so when you set this up here, what REW does is it has a really nice calibration procedure, and it says things like, oh, let's go take a measurement without the test leads hooked up. All that means is that don't plug anything into the little jack here. And then it says, oh, let's take a measurement instead with the test lead shorted. So what that means is you take your little adapter, and instead of having the resistor there, you have a little piece of hookup wire in its place, and you short the pins out. And you take a measurement. And then it says, go take it with a known resistance. The same exact thing that you made before with your 10.2 ohm resistor, you take it with that. And you tell it that it's like that ohm rating. And that's it. Once you have that, you can then just hit measure, and in the impedance tab there, goes and does the measurement. Boom, that's exactly how those plots I was showing you before were made. If you want to then come up with the plots to say how much of an impact is that going to have, what I'm showing you here, you can have REW actually output just as a text file or something like that, the measurement that it's made, and that's what led to the frequency, the Z ohms, the phase degrees. And now here is the simulation that I've done to come up with the impact of each of these different impedance values. So here's then the formula that's in the 3 ohm one. The 3s here are just because it's 3 ohms. In the 10 column, those are 10s in those two spots. And then you see this weird B2727. All that is that's actually the impedance, column B, of 1000 hertz, which is exactly then how I did the norming before to actually get it to 1000 hertz. So honestly, by the time you've gone and measured the output impedance just with this, you're just a couple more connectors away, depending upon your rig, couple more connectors, 100 ohm resistor, and some hookup wire, and you can now accurately measure the impedance of any IEM or headphone that you might have and see what impact this would be? Not exactly a tough thing to do. All right, and with that, I hope you learned something about impedance.